Welcome to Chapter 8, Cognition and Language. Slide 2. Try to find the white bird. Pretty easy, right? Yep, keep this in mind. Try to find the bird facing the opposite way. It takes maybe a little bit more time. Okay, keep that in mind. Slide 4. When the name of a color is the color that it's naming, it's very easy to tell what the color is of each of these words. The red is red. The word green is green, etc. Slide 5. But when the name of a color is in a color that is not the name, it makes it a little more difficult and takes a little bit more time to say what color is the word red. Look at it and you want to say red because that's what the letters are saying, but it's actually green. And green is actually yellow. You can keep this in mind. Slide 6. So these topics and more are going to be the focus of this lecture. We're going to be covering 3 main topics. First, we're going to cover what cognition is and the importance of attention and categorizing. Then we'll move on to problem solving and decision making. And then finally, we'll talk about language and how important cognition is in the role of language. Slide 7. So let's review. Here's a slide from the first class demonstrating how the focus of psychology has, like a pendulum, swung from the mind to behavior and back. We started with a focus on the mind and introspection, as used by Weber in the structuralist school, William James in the functionalist school, and Sigmund Freud with his psychoanalytic theory, and we're going to discuss him in detail later in the semester. This focus on the mind is responsible for the beginning of research in the field of sensation and perception, which we've gone over. The focus then swings away from mind to behavior, as the behaviorists flex hard in psychology as a reaction against mentalistic ideas. The behaviorist contribution to psychology was a deep understanding of simple learning concepts, and we went over that when we went over learning. And just as behaviorism was a reaction against mentalism, the cognitive revolution was a reaction against behaviorism. With the computer as inspiration, cognitive psychologists moved forward with an information processing model of the human mind to explain memory, thought, and language. Slide 8. Here's an information processing model for memory used in the last lecture. The topic we'll be covering in this lecture very much takes place in the working memory of short-term memory, relying on an interaction with long-term memory to shape expectations and perceptions. Slide 9. Cognition means thinking and using knowledge, and it begins with attending to something and categorizing what it is. This works for thoughts and language. Researchers learn about cognitive processes they cannot observe by measuring the speed and accuracy of responses to get an objective measure. This is because you can't just ask someone what they're thinking and get reliable data. The decisions and choices we make and the preferences that we have are based on mechanisms to which we are completely blind. This is called choice blindness. Slide 10. Choice blindness is exposed in experiments like this. Real quick, you're asked to choose which of 2 picks is more attractive, then explain why you made your choice while looking at the photo you chose. Unbeknownst to you, you're handed the wrong photo. So while you're explaining why you chose that picture, you're holding the picture that you did not choose. Again, let's follow it through the slide we have here. A participant is asked to choose between 2 photos based on attractiveness, as shown in frame A. The participant chooses, as shown in frame B, the picture on the left. Frame C is a poor demonstration for what's happening. It is a sleight of hand trick where the participant is handed the photo of the person on the right, not the person on the left. And this is exposed in frame D, which is supposed to show someone justifying their choice of why they chose that picture of who is more attractive, while they are holding the card of the person they did not choose as being more attractive. The whole point here is that most of the time we are oblivious to why we make the choices we do, to the point where we will justify a choice we didn't make. Slide 11. Attention is defined as the tendency to respond to and to remember some stimuli more than others. Some stimuli grab our attention automatically. Psychologists call this bottom-up processing because the peripheral stimuli control it. Magicians use this tendency. A magician pulls a rabbit or a dove out of a hat, and the surprised viewers automatically watch the rabbit hop away or the dove fly away. During the brief time that the attention is occupied, the magician sets up the next trick unnoticed. We also can control our attention, deliberately shifting it from one item to another in a process called top-down processing. To illustrate this, fixate your eyes on the X in the center of the graphic on the slide. Then, without moving your eyes, read the letters in the circle around it, clockwise. As you see, it is possible to control your attention without even moving your eyes. Slide 12. So, this slide from the beginning of the lecture, I asked you to look for the white bird. How easy was that? To illustrate how an unusual object draws attention, I asked you to find the whooping crane within a flock of sandhill cranes. When anything differs drastically from items around it in shape, size, color, or movement, we find it by pre-attentive processes, and that just means it stands out immediately. We don't have to look for it. We automatically find it. Slide 13. And in this slide from the beginning of the class, I asked you to find the bird that's facing the wrong way. More specifically, you're looking for the marbled godwit that is facing to the right. Yeah, that's the name of these birds. In this instance, you have to check each bird separately depending on where you start scanning. The more birds that are present, the longer you probably need to find the unusual one. For this, you have to rely on attentive processes, ones that require searching through the items in a series. And the goal here is to just have you experience what it's like to engage in the bottom-up versus top-down processing, right? Whereas Waldo is top-down processing, seeing somebody running down the street on fire is bottom-up processing. You're going to notice that. Slide 14. Much evidence indicates that attention is limited, as if various items were trying to get through a bottleneck that permits only a little to pass through at a time. If 2 or 3 objects flash briefly on a screen, you can identify their colors. If 6 objects flash on a screen, you still know the colors of only 2 or 3. You can more effectively attend to a couple of items at the same time if they're not similar to each other. The apparent reason is that 2 similar items activate overlapping populations of neurons in your brain and therefore interfere with each other. You can easily do things at once when 2 activities are highly compatible, such as walking and chewing gum. However, people who try to quote-unquote multitask, doing 2 or more unrelated tasks at a time, they're often more impaired than they realize. They're just doing a half-assed job on both of them. Even when you're only doing one task, your attention level varies. While your mind wanders, you're thinking about something unrelated to the task, and your ability to process the relevant information decreases. You've decreased your bandwidth by thinking about something else. And for this reason, mind wandering interferes especially with performance on difficult tasks. Examples of the attention bottleneck include the Stroop effect. This is the process of trying to read the color that the letters that are the name of a color are currently written in. So because words grab our attention, it's very difficult to say that the word green is in the color blue, and that the color blue is in the color red, and that the color, and that the word red is in the color green. It's much easier when they're congruent. Another example of attention bottlenecking is change blindness, which is the failure to detect changes in parts of a scene. We often fail to detect changes in a scene if they occur slowly or during an eye movement. Slide 15. So here's the Stroop effect again. if I asked you to read the color of the letters for each of the words as fast as you can, how good do you think you're going to do? I'm going to give it a shot right now. I'm going to go from left to right. Okay. So I'm starting with the word red, top row, and I'm going to the word pink, top row. And then I'm going to keep going row by row. Here we go. But I'm going to say the color. 1, 2, 3. Green, yellow, white, pink, red, blue, red, yellow, green, blue, red, blue, green, red, pink, blue, yellow, pink. I can't. Green, red, blue, orange, I think maybe. Red, green. I sucked at that. I could edit this to make it sound like I went faster. I should edit this to make it sound like I went faster, but I won't. That's as fast as I could do it. I'll bet you if they were printed in the congruent color that the label, the letters were spelling out, I would be able to blast through that. Slide 16. In the example of change blindness, you've seen this, right? There's YouTube videos dedicated to this. There's two guys. One of them asks somebody for directions, and then something gets in the way, and then a completely different person who is behind the thing that gets in the way replaces the dude who was asking for directions initially. And the person who's giving the directions does not notice that he is now speaking to a different person than initially asked him the question. And this is laid out with all of these panels. In the top left panel, person 1 is asking for directions. In the top right panel, that is interrupted. In the bottom left panel, someone completely different but dressed similarly is there receiving the directions that were asked for by the first person. And then the bottom right panel is the two different people, just so that you can see that it was indeed two different people. Slide 17. Well, sometimes there are some difficulties with attention. So let's talk about attention problems. Obviously, people vary in their ability to maintain attention, as in anything else. Attention deficit disorder, or ADD, is characterized by easy distraction, impulsiveness, moodiness, and failure to follow through on plans. Attention deficit hyperactivity disorder, or ADHD, is the same, except with excessive activity and fidgetiness. The symptoms vary considerably in type and intensity. Both children and adults with ADHD show mild abnormalities in certain brain areas on average, especially in the frontal cortex. It's also reported that people with ADHD have greater overall brain activity, implying a lack of inhibitory transmissions. All of the reported brain abnormalities vary from one person to another. Slide 18. The problem with people with ADD or ADHD is not an inability to pay attention. People with ADHD easily pay attention to anything they care about. The problem relates to shifting attention quickly and appropriately. Two tasks sensitive to attention deficit disorder are the choice delay task and the stop signal task. In the choice delay task, the question is under what conditions someone will sacrifice a reward now for a greater one later. On average, people with ADHD are more likely than other people their age to opt for an immediate reward. So as an example, you can imagine the marshmallow test, right? If you're not familiar with the marshmallow test, there was a famous experiment done. I'm probably going to talk more about this when I speak about morality. It was a popular test done with little kids. Give them a marshmallow and say, hey, you can eat this right now. But if you don't eat it for 5 minutes, I'll give you 2. And then they're left alone in the room with that one marshmallow. Well, of course, it takes a whole lot of delay of gratification to look at the thing that you could have right now and know that if you wait, you get 2 of those things. That's hard for all humans. We are all short-term oriented as far as gratification. Whereas in the stop signal task, one signal calls for a response and a second signal calls to cancel that first signal. The question is, under what circumstances a person can inhibit the response? For this, I ask you to just think of the classic game red light, green light. And if you don't know what that is, somebody yells out green light and a bunch of kids run towards a target. But that target is a person who also has the ability to say red light. So every once in a while, they'll do a green light, red light, The kids have to stop, start, stop, start, stop, start. And that ability to stop and start is this stop signal task made into a game because it's fun. Most people with ADD or ADHD have trouble inhibiting their responses after short delays. Slide 19. The next important part about cognition is categorizing. Putting things into categories makes our thinking more efficient. For example, what you learn about cars tells you what to expect of cars in general. However, categorizing sometimes proves a disadvantage. If you categorize some politician as member of the party I oppose, then you're inclined to oppose every idea that politician advocates. In short, categories are necessary, but heavy reliance on them is sometimes misleading. Many concepts are hard to define. You can probably recognize country music, but can you define it? What's the border between being bald and not bald? Is a taco a sandwich? Eleanor Rosen argued that many categories are best described by familiar or typical examples called prototypes. After we identify good prototypes of country music or bald person, we compare other items to it. Depending on how closely something matches, we call it a member of that category, or a non-member, or a borderline case. Take the example on the slide. We have a flower, we have an automobile, and we have an escalator. Which is a vehicle? Are they all vehicles? Okay, well, if you're going to say that, then which is the member of the category? I guess that would be the car. The borderline case maybe is the escalator. And flower, I would say, is a non-member. But if something was traveling on the flower as the flower traveled, it could be considered a vehicle, maybe, question mark. But you see how, like, categorizing, like, once you get down to the minutia, everything becomes fuzzy. Something to think about. Slide 20. We link a word or concept to related concepts. The process by which the activation of one concept activates or primes related concepts is called spreading activation. For example, if you hear flower, you're primed to think of rose or violet and other flowers. If you also hear red, the combination of flower and red primes you to think even more of rose. The idea of priming is a concept analogous to priming a pump. If you put some water in the pump to get it started, you can continue using the pump to draw water from the well. Similarly, priming a concept gets it started. Reading or hearing one word makes it easier to think or recognize a related word. Seeing something makes it easier to recognize a related object. Priming is important in language. When you read a word that you barely know, or have trouble hearing a word someone has said, the context helps you understand it if the preceding sentences were about closely related concepts. This underlies the idea from last lecture that we reconstruct our memories, and in doing so, can predictably and reliably remember words that weren't said. Well, that doesn't just apply to words, it applies to concepts as well. The example on the slide shows how someone like Joe Biden, President Joe Biden now, I made this slide 4 years ago, who is prone to putting his foot in his mouth, suffers from foot-in-mouth disease because our conceptual network recognizes the wordplay of foot and mouth disease with foot-in-mouth disease. And it could be said that the phrase foot-in-mouth disease is a portmanteau or a combination of foot and mouth disease and putting your foot in your mouth. And those two things were primed to go together because of our conceptual networks. Slide 21. Lest we forget the long-term semantic networks of last lecture. And then just blast through all the way to slide 28, where we could logically start with animal and end with pair based on the associations of our semantic and conceptual networks. Slide 29. Let's move on to problem solving and decision making. Slide 30. Daniel Kahneman described human thinking in terms of two systems. We often make decisions quickly and automatically using System 1, and System 1 generally proceeds without much effort. When we recognize a problem as being more difficult, we do calculations. ponder the evidence, or in other ways engage effortful processes. This uses System 2, which relies heavily on working memory. And if your working memory is already loaded because you're trying to remember something else, you tend to fall back onto System 1, because System 1 saves time and energy. We rely on it whenever we can. System 1 thinking relies heavily on heuristics. Heuristics are strategies for simplifying a problem and generating a satisfactory guess. Heuristics provide quick guidance when you're willing or forced to accept some possibility of error, and they work well most of the time. I think of heuristics as mental shortcuts, whereas in many cases, System 2 thinking solves problems by using an algorithm or an explicit procedure for calculating an answer or testing every hypothesis. This is very different than System 1 thinking. System 1 thinking is reflexive and immediate. System 2 thinking is slow and deliberate. Slide 31. So, let's give some examples of what System 1 and System 2 thinking feel like. I have some quizzes here, and I'm going to try to fool you. Let's look at the first one. A bat and a ball cost $1.10 in total. The bat costs $1 more than the ball. How much does the ball cost? Immediately. What do you think? As fast as an answer as you can give. Okay. Most people say the ball cost 10 cents because their quick and dirty System 1 thinking just subtracted $1 from $1.10 because they saw $1 more, right? In reality, the ball cost 5 cents. How's that? Because if the bat costs $1 more than the ball and the ball costs 5 cents, that means that the bat costs $1.05. And 5 cents plus $1.05 is $1.10. Now, if you didn't get that right, don't feel bad. I didn't get any of these right the first time I heard them because they demonstrate fast thinking. So now that you know what the trick is, see if you can engage in deliberate thinking for these next two questions. Okay, moving on to number 2. If it takes 5 machines 5 minutes to make 5 widgets, how long would it take 100 machines to make 100 widgets? Okay, System 1 thinking is saying 100 minutes to me, right? But it doesn't matter because the answer is still 5 minutes. In the example above, it doesn't imply that each machine takes 1 minute to make one widget. It implies that each machine takes 5 minutes to make one widget, and depending on the amount of machines, that's how many widgets you will get at the end. So 100 machines are still going to take 5 minutes to make a widget each. It's just that you have 100 machines, so you're going to make 100 widgets. All right, let's move on to the next one. Remember, try to be deliberate about what your answers are. System 2 thinking. In a lake, there's a patch of lily pads. Every day, the patch doubles in size. If it takes 48 days for the patch to cover the entire lake, how long would it take for the patch to cover half the lake? Well, System 1 thinking, it wants me to divide 48 in half and say 24 days. That doesn't make sense because we're talking about something that doubles every day. So if it doubles every day, the day before day 48, it was half the size as possible, right? So that means it would take 47 days for it to cover half the lake. See, these are tricky. These are tricky. We are all prone to these. This is why we are predictably irrational. But don't get me started on that. Slide 32. In here we have 2 different kinds of mental shortcuts or heuristics. We have the representative heuristic, which if something resembles members of some category, we usually assume it too belongs to that category. However, that assumption is risky if the category is a rare one. The example they use in the slide is if something looks like it might be a UFO, you just decide that it is. Well, yeah, it doesn't work like that. You don't get to make those decisions. And then there's the availability heuristic, which is where we generally assume that the more easily we can think of examples of some category, the more common that category is. However, this heuristic misleads us when items in rare categories get much publicity. And this one has to do with the classic, fear of flying in airplanes. One explanation for this fear is that people remember more reports of airplane crashes than car crashes because they're reported more frequently on the news. So they think that air travel is more dangerous, even though it is demonstrably not. Slide 33. In addition to sometimes relying inappropriately on the representative heuristic and availability heuristic, people make other errors. On difficult questions, most people are overconfident in their answers. People also tend to look for evidence that confirms their hypothesis instead of evidence that might reject it, a tendency known as the confirmation bias. Further, people answer the same question differently when it is framed differently. Here's an example. A company that provides health insurance will charge higher rates to overweight people. If they describe it as a discount for lower weight, people like it better than if they call it a penalty for higher weight, even though the effect is the same. Also, people sometimes take unpleasant actions to avoid admitting that previous actions were a waste of time or money. This is called the sunk cost effect. And the example given for this is, if you buy 2 tickets accidentally for the same weekend, and one of them is $50 and one's $100, you're going to go to the place that cost $100 just because you don't want to feel like you lost money, right? That you sunk cost. But what if the $50 trip's way more fun? Well, then you're actually sacrificing fun to psychologically satisfy this sunk cost effect. It doesn't make sense. Just consider the money lost and go have fun. Slide 34. Although all of us make mistakes in our reasoning, some people develop expertise within a given field that enables them to solve problems quickly with a minimum of error. Reaching that point requires much effort. In fields as diverse as chess, sports, and violin playing, expertise requires about 10 years of intense practice, or about 10,000 hours. However, due to individual differences, 2 people who practice a skill such as piano or chess for the same number of hours are not necessarily equal at the end. In general, those who learn faster in school also develop expertise faster. For practice to be effective, people need feedback based on the practice. People who got good feedback have a chance to improve with practice. Slide 35. What sets experts apart from others is that they can look at a pattern and recognize its important features quickly. So for instance, if a master or an expert chess player looks at a chessboard in the middle of play, it makes perfect sense to them. They will know whether it is the opening gambit or the end game or the middle game. They'll have it figured out. But here's the super funny part. If you randomly put chess pieces on a chessboard and ask a chess master or expert to memorize it, they don't do any better than regular people. The placement of the pieces has to be within their already existing system of expertise, and they can tell you exactly what's going on. But if you just put random pieces on the chessboard, they are just normal humans. Moving on. Developing skill at a task aids performance of similar tasks, but it seldom helps with dissimilar tasks. But it can. So there's a thing called near transfer and far transfer. Near transfer is where the benefit to a new skill is based on the practice of a similar skill. So for instance, training in a certain coding language helps learning future programming coding languages. Far transfer, which is a little bit more rare, but think of it this way. You can benefit, from practicing something less similar. So knowing about geometry, being trained in geometry can help you visualize the path of a barbell should you be somebody who works out and does cleans and jerks. I know, that's a little bit of a stretch, but there's research to support this. Slide 36. Let's talk about language. Slide 37. Every species of animal has ways of communicating, but only human language has the property of productivity, the ability to combine words into new sentences that express an unlimited variety of ideas. We do not memorize all of the sentences that we use. Instead, we learn rules for making and understanding sentences. The famous linguist Noam Chomsky described those rules as a transformational grammar, a system for converting a deep structure into a surface structure. The deep structure is the underlying logic or meaning of a sentence. The surface structure is the sequence of words as they're actually spoken or written. According to this theory, whenever we speak, we transform the deep structure of the language into a surface structure. Slide 38. Bonobos have been more successful with language than common chimpanzees due to several reasons. Apparently, bonobos have a greater predisposition for this type of learning. Also, they learn by observation and imitation, which promote better understanding than the formal training methods that previous studies used. Finally, the bonobos began their learning experience early in life. You may be asking why we're talking about bonobos. In case you didn't know, bonobos and chimpanzees are humans' closest relatives genetically. That is, according to the genetic tree, right, the evolutionary tree, bonobos and chimpanzees are equidistant from us. They are our cousins genetically. So they have very similar brains to us. That's why this kind of research is done. This is the comparative psychology that I was talking about from previous lectures. Noam Chomsky and others have argued that the ease with which children acquire language indicates that they're born with a predisposition that facilitates language learning. Still, the exact nature of that predisposition is uncertain. He called it a language acquisition device, as if there was an actual built-in mechanism, a device for learning language during a critical period. We all now understand that there is no such device. It's an as-if model. It's as if we have a language acquisition device. Slide 39. And Table 8.2 lists the average ages at which children reach various stages of language ability. Remember, these are averages, and children vary considerably. Progression through these stages depends largely on maturation. Deaf infants babble as much as hearing infants do for the first 6 months, and then they start to decline. At first, hearing infants babble only haphazard sounds, but soon they start repeating the sounds they've been hearing. By age 1, an infant babbles mostly sounds that resemble the language the family speaks. By age 1.5, most toddlers have a vocabulary of about 50 words, but they seldom link the words together. For example, a toddler says daddy and bye-bye, but rarely bye-bye daddy. Toddlers also sometimes combine a word with a gesture, such as pointing at something while saying mine. Of course, everything's theirs. The word and gesture constitute a primitive kind of sentence. Children who convey much information by gesture alone or word plus gesture by age 1.5 are likely to develop better than average vocabulary and complex sentence structure by age 3.5. By age 2, children start producing telegraphic phrases of 2 or more words, such as more page, meaning maybe read some more to me, or all gone sticky, like my hands are now clean, right? Or all gone outside, when somebody has closed the door, right? Who doesn't want to say goodbye to outside? Bye-bye, tree. By age 2.5 to 3 years old, most children generate sentences, but with some idiosyncrasies, right? So the sentences of a 2.5 and a 3-year-old are a little bit different than the ones of adults. They don't quite have the plural thing correct or the conjugation of verbs, but they're sentences nonetheless. They eventually get there. Slide 40. In context not only determines how we interpret a word, but also primes us to hear an ambiguous sound one way or another. Understanding a sentence depends on your knowledge of the world and all the assumptions that you share with the speaker or writer of a sentence. Some grammatical sentences are almost incomprehensible. One example is a doubly embedded sentence, a sentence within a sentence within a sentence. The dog the cat saw chased a squirrel. The squirrel the dog chased climbed the tree. In the first sentence, the cat saw the dog is embedded within the dog chased a squirrel. In the second, the dog chased the squirrel is embedded within the squirrel climbed the tree. And all of this just to demonstrate that we understand language on the fly, but there are circumstances in certain kinds of sentences, like embedded sentences, that make understanding language a little bit more difficult. Moving on. Because you've been reading for hours a day, almost every day since childhood, you've developed expertise in reading. You recognize words instantly. This is part of what makes the Stroop effect so powerful. We very much want to read the words. Word superiority, baby. Consider the following experiment. An investigator flashes a letter on a screen for less than a quarter second, shows an interfering pattern, and asks, was the letter a C or a J? Then the experimenter flashes an entire word on the screen under the same conditions and asks, Was the first letter of the word a C or a J? Which question do you think is easier? Most people identify the letter more accurately when it is part of a word than when it's presented by itself. This is known as the word superiority effect. When we see words, we just immediately process it as a chunk of information. But what accounts for this word superiority effect? Well, according to one model, the one we'll be covering in class, our perceptions and memories are represented by connections among units corresponding to sets of neurons. Each unit connects to other units. Any activated unit excites some of its neighbors and inhibits others. Suppose units corresponding to the letters C, O, I, and N are moderately active. They excite a higher order unit corresponding to the word coin. Although none of the four-letter units sends a strong message by itself, the collective impact is strong. The perception coin then feeds activation back to the individual letter-identifying units and confirms their tentative identifications. I know that that was a long walk, I'm sorry, but all of this to say more letters in the words provides more activation, which might be why our brain processes them as more important information. Slide 41. And students of language distinguish between phonemes and morphemes. A phoneme is a unit of sound, such as an F or a sh. A morpheme is a unit of meaning. The example given here, we have the word shamelessness. Phonemes, being that they are just units of sound, we have 9. We have the sh of the SH, the A, the M, E is silent, the L, the E, the double S is one chunk of sound, an N, an E, and an SS again. So that's the shamelessness. 9 phoneme units. But morpheme units are units of meaning. So shamelessness is actually 3 morphemes. We have the word shame, we have less, which means that there is no shame, and then ness, which means that this is now an activity that could be applied to somebody else, or a label that can be applied to someone else. Shamelessness. So morphemes help us break words into meaningful parts. Slide 42. And there you have it, ladies and gentlemen. We are done with cognition and language. Purposely made this a little bit shorter, give you a breather before we move on to intelligence, next chapter. I will see you next chapter, but before I do, let's go over what we talked about. We started with an introduction to cognition. I defined it. We talked about attention and how important it is, categorizing and how important that is. We talked about problem solving and decision making. And then we moved on to language. I'll see you next chapter.